Yeah, so thank you for inviting me, the organizers. This is a new paper. It just came out like 2 weeks ago, so it's a new talk. So please ask questions. I'm super interested in this. I think it's a cool area. Not a lot has been done. And this has been with some collaborators, Elliot Paquette, who's at McGill, Jeffrey and Lechao, who are both at Google Deepmind. Okay. So like a year and a half ago, like a bunch of things changed in the world of machine learning, right? We saw ChatGPT come out and these large language models. And one of the kind of things from a theory point of view that started to change was that, well, we used to kind of think that data was sort of our limitation. That like fix some data, you know, your data, that's the thing which like prevents you from really optimizing further. Why is this? So this leads to overparameterization, generalization, things, stuff like that, excess risk. But then ChatGPT and large language models and all these foundational models, which are gigantic, came out. And what ended up we saw is that, at least for the current moment, data is not a problem anymore. Data is sort of infinite. You have the whole internet, okay? So what is actually really, really preventing us nowadays from actually solving the problem is actually not data as a limitation, but compute. That because compute, we don't have a lot of it, it's sort of the main thing which stops our optimization from happening. Okay? So this is the idea that we're in an infinite data regime. So that's always what I'm going to be working in this talk. And the idea is, for a given compute budget, how do we best allocate our resources? Okay, simple question. Okay, what does that mean? Let's try and formulate this as a math problem, okay? And this is going to be based off of like chinchilla paper, if you guys have seen. Okay, so what's the idea formally? The formula is you're minimizing some loss, P of x, okay, where x lives in some RD space, D is the number of parameters. And so the idea is that we can do a simple computation cost, which says that the compute cost, or the number of flops, is roughly the number of iterations of your algorithm times by the number of parameters D. Okay, you can add batch in here, it won't do anything, but okay. We can, okay. Okay, so what was observed? This was observed in chinchilla. Why is this so important? It's because nowadays, right, what you have to do is like someone says you have $1 million, right? What are you going to use it on? You don't use it on data. Data is freely available. You use it on compute. And so they want to know how to choose their parameters. So what was observed was the following. So what they did was they said, OK, let me just run SGD, or some stochastic algorithm, on this for many, many different parameters D. So many different parameters. OK? And because I have a compute cost formula that says flops is equal to number of iterations times parameters, I can express the loss as actually a function of flops. And when you do that, you get a curve. You get these colored curves, ignore the red, which look like this. Okay? And so what is the idea? The question is, if you fix your flop compute, again, I'm assuming infinite amount of data, how do I choose my D so that I get the best loss? Okay? Here, D star you can view is in the argmin of this function. OK, so let's examine this a little closer. So let's think. So if I fix my flops here, that's like I'm fixing this gray dashed line, right? So OK, what happens? Let's take D is equal to 1600. That's the purple curve. Well, parameters are pretty small. That means I can run it for very long, right? Run it for a very, very long time. But there's a problem, which is that because I don't have very many parameters, my model is not very expressive. And as a result, I flatten out. And so I'm wasting compute, right? Because I somehow flatten out. Okay? So, OK, so you increase D. So maybe I choose D is equal to 51,000. Okay? That's that light green curve. The problem with that is that, of course, now D is very big. So my cost is very large to run, and therefore I can't run it for very many number of iterations. And so I don't solve enough of the problem for that fixed flop, right? I just can't run the algorithm for very long. I'm restricted there. And what you see for this gray line here is that the best choice is roughly, I think, 6,400. Okay? And now you do this for every flop value. And what we saw is this red curve. And this is what is called the compute optimal curve. Okay? Because it says, OK, for any flop, here's how I can choose things. And the idea is you would want to predict this, because this is too expensive, this procedure. I can't just run Ds. I can't run my algorithm over many, many Ds and then try and take the optimal one. That's too expensive, right? You would want to be able to predict what that curve is. Yeah?
So there's the over-parameterization phenomenon.
Yes.
So meaning that, let's say, if you have very high dimension, these models can generalize better type of thing. Is there a way to incorporate that?
OK, so this is this idea at the beginning. The problem is we're not even close at the moment to over-parameterization. It's sort of like compute is stopping us so early that we're not even getting to generalization performance ideas or over-parameter. We can't get that far. We're constrained by the compute. That's sort of the thing. That's not to say it won't eventually go, but it's like maybe a different idea what's happening. But you can try and incorporate it too in there. Is the question clear, or problem clear? OK. So why was D equals 6,400? Well, this problem illustrates that the compute optimal curve is kind of constrained by capacity. So one thing that can create this line is how expressive is your model. Okay? But that turns out not to be the only thing. Okay? Yeah? Yeah.
So you're assuming, though, am I correct that you're essentially assuming that the performance at a fixed number of flops, it doesn't matter. You're saying, I could have a small model with many iterations or a large model with a few iterations. You're assuming that if I fix the compute budget, performance is the same.
No, no, no. I'm trying to choose this following. I'm trying to find the D that minimizes the loss as a function of flops over D.
I see. So it's really a function of the number of iterations.
It's a function of the function of the number of iterations, but your loss is also a function of D. Hidden in there, it's a function of D and the number of iterations.
So when you're saying argument here, you're really, for each D, you're getting a different choice of P. Is that right?
No, no. This is maybe you have your loss is a function of your iterates and D.
Yeah.
Then you replace number of iterations by flops over D. So this is a function. You can express your loss as a function of flops over D and D. And you're just trying to find the argmin. Yeah. Kind of fun, right?
Yeah, so you're sort of like taking, the values for sort of different choices of K and P.
Exactly. That's exactly right. And the reason you want to do this is because you want to predict ahead of time, right? You want to say, here, someone gives you, $1 million. You use it on flops. How do you choose D? And you can use it from this curve. Yeah. Wow, I'm not going to get through my slides. OK, yeah.
So maybe because I'm really late to explain it, but why are the curves looking exactly like this? Because this is kind of nice, but why is there flat in the beginning? Whenever we see the plots of loss when we run things, right, it always kind of drops very quickly first.
Yeah, it's because you're doing it with iteration counts. When you put in flops here, it changes in D. And your loss level goes to as a function of D.
Sure, yeah, but...
So then when you scale, no, this is actually, when you scale it, you get this picture.
Yeah, but then it wouldn't be dropping off like this. That's what I'm saying. So if it's really per iteration, sorry.
It's not per iteration, so that's right. It's flop.
Right, exactly. Right. So if it's not per iteration, then I don't understand why it becomes really faster then. So the number of iterations, so each iteration brings more loss, decrease in the beginning than in the end.
Yes.
Each iteration costs the same with respect to D. So,
and no, because the limit level that you converge to is a function of D also.
Okay, but why is it speeding up?
What?
Why is there like, so first it's slow and then it drops?
Because your iterations is a function of flops. So when you go down, it scales. Oh.
It's not time on the x-axis.
It's not time on the x-axis. This is flop count. Flops is not time. When you plot it as a function of compute, you get curves which look like this. On the time scale, they look exactly like you said. But on a flop scale, they do not. Yeah. It's not the same. It's not the same. Yeah. Yeah.
I guess it's a different for each curve, it is a fixed D, right?
Yeah, for each curve, it's a fixed D.
So if I look at a fixed curve, it is time. Yeah.
Yeah. I mean, the reason that you see this behavior is because the limit level depends on D.
Sure.
Yeah, but it's still speeding up though.
It is. It looks like it is, right? But flops is, you're writing flops as k times d, so this is k times d. So you're scaling your number of iterations by d.
Yeah, but I guess like just look at the first, like let's ignore all the curves. Let's
Yeah.
just look at any one curve, right?
Yeah.
Even for one curve.
Yeah,
Right?
yeah. So then when I scale it,
scale the x-axis, so it's just time.
yeah, and then all these curves will line up on each other. Then they're lined up. But the problem is that I scale by iterations is equal to flops. Flops is iterations, right? So if I drew this on here, the scaling by D changes the shape of this curve. If I put it back in iterations, it looks identical to what you guys just said. All of these curves would line up. The problem is when you convert, it changes. That's why. It like scales. Yeah. Not going to get through. OK, we're on the first slide. Yeah. By the way, just to point this out, this picture was observed in language models. This is what people have been talking about when they mean scaling. This is the picture. Yeah.
Is the k also depend on d?
So k, you fix, essentially yes. Because you write flops is, OK. K will eventually depend on D, yeah. Because the limit level, how long it takes to get to a limit level is D dependent. Right? Okay. I will tell you that if you do this, you will actually, this is what you see when you do this plot. This is a known phenomenon, okay? It's in large language models, it's everywhere. Okay, so what are we going to do? So the idea here is that we're not going to study language models. They're too complicated. What we're going to do is we're going to find an easier model that we can completely analyze. OK? And we're going to do it. We're going to solve that model completely with one-pass SGD. We'll get theoretical expressions. And I'm going to use two different parameters to control everything. I'm going to choose a data complexity, which is going to be modeled by alpha, and a target complexity, which is going to be modeled by beta. And what we're going to see is, depending on the target complexity and the data complexity, we're going to get 4 different qualitatively loss curves, if you want. They're going to look different. Okay? The +3 is because we're going to also get quantitative ones that differ, okay? And they're all going to be dependent on the choice of alpha and beta. What's going to constrain us, okay? Well, there's 3 things we're going to see. We're either going to see a model constraint, that is, capacity is the thing which limits our compute optimal. Okay? That is, we go down, we wait till we hit the limit level. As soon as we hit the limit level, we should have increased D. Right? That's right. Okay? That's one thing. But we'll also see that poor feature embedding can cause problems. what this is saying is that, well, what can happen is that if your signal gets a little fuzzy, then when you go into that fuzzy region for your signal, it starts to slow down in training. And once that starts to happen, you might want to increase D. You might not want to solve through it, even though you could. You could go solve through it and decrease all the way down to the loss. You could do it, but you don't want to. It's more compute favored to increase at that point. I'll explain a little bit more about it. The other thing is you can get algorithmic constraint. That is to say, SGD, it slows you down in training because of the noise it produces. What's amazing about this is that for a large portion of the alpha-beta phase plane, you see a universal scaling law. That is to say that the D star, the argmin, the best thing you can do as a function of flops is just to take flops to the 1/2. It's amazing. It's some complicated formula, and you just end up with f to the 1/2. Okay? And this is basically theoretically validating some work in Chinchilla, which was done on empirical stuff. OK. I'll do it right here in a second. So how do we do it? What's the simplest model? So we're going to steal a model we've seen. It's basically a random features model. So we're going to take our data A to live in RV, and we're going to embed it into RD via a random matrix. And we have a target beta. So what I mean by one-pass SGD is that at each iteration, I just generate a new data point, because I have infinite data, and I update stochastically based on that one data point. Only based on that one data, so it's stochastic. What do I need to assume? W here should be a random matrix with entries Gaussian. I'm just going to make that. Okay. My model complexity alpha is going to be modeled by assuming that that my data A satisfies a power law distribution. This is important. This is what data looks like. Where people assume. Mahoney actually kind of hinted at this too. Okay. For my targets, I'm also going to assume a power law distribution. And because I'm in language models, I'm going to think of V really big compared to D. So this embedding D is allowing me to vary over different parameter sizes. And what's going to be important is this K hat, which is D, W, W transpose. D is just a diagonal where I put along the power law. Okay? Alpha is data complexity. Beta is target complexity. What? K hat is just D, W, W transpose. W is a random matrix, Gaussian. D is a diagonal matrix. This is random features with power law, if you really want. OK, so what you do is then, well, OK, you just plug into a loss. I'm just using the random features as my loss. I have my compute optimal formula. So my compute optimal will be to minimize D over this loss, where I plug in F over D. My loss is also a function of D. And what you're going to see is that the optimum looks like some flops to some power. And the optimal loss is also some flops to some power. And the goal is to find the power, sigma 1, sigma 2. Previous work has looked at this. I think people in this room have looked at this sort of in a gradient flow version of it. There's been some other work along this line, usually not with the compute constraint. It's because this model exhibits this type of scaling law, which is what has been shown in the language models. That's where it comes from. So it's a nice model to work with. OK, so what do you do? Well, it turns out that if you just condition on the random matrix W, and you solve this thing, taking the expectation over the data, what you end up with is that the expectation conditional satisfies a convolution Voltaire equation, okay, where I have a forcing function in kernel. The forcing function is like running gradient descent. And the kernel part is like the SGD noise. And the forcing function, if you look closely, is a function of this k hat, which is a random matrix. OK. Now we're getting into random matrix theory. Oh, sorry. Maybe I'll skip that. Now we'll get into random matrix theory. OK, I live with a random matrix theorist. Here's what they would say. K hat is random. So what do? You go new school, and you take the resolvent and find the deterministic equivalent of it. And remove the randomness from the problem. And you can do that. And what you get is, of course, some fixed point equation that has to be solved. And here's the resolvent, the deterministic equivalent. So you replace this k hat with the resolvent of k hat, or the deterministic equivalent of the resolvent of k hat. And what you end up with is, again, a convolution Volterra equation with a forcing function in kernel that's completely deterministic now. Okay.
Is it like the expectation of the whole dynamics, or is it just?
No. Because, OK, it's not, because this is not equal. Like, the expectation over W is not actually this quantity, but you think of it like it is. But it's not that. Random matrix theorists will tell you, deterministic equivalent, technically different. But it's got that feeling to it. So these two are close. And you can see it when you plot. If you plot flops on the x and training on the y, the dashed lines are the Volterra equation from the deterministic one, which you can solve. And the color lines are SGD.
So if you have an almost sure limit, for example, then you can argue that. So
it's going to be with some dimension. So as d gets big, you have to do this. So that the two are close.
Basically, you have a random object and you have a deterministic approximation, right? They are close in some sense.
In some sense.
And what is that sense?
OK.
It's complicated.
So we actually didn't do this because it would take about 100 pages. This is all from random matrix theorists, if you knew this, because you have to prove the deterministic equivalent formulas, which are annoying. It should be something like what we did before, so some with high probability sort of brown. Yeah, that gets better in D, kind of a thing, as D gets big. Just to point out that it does work, you can actually plot this, and it just works. But this isn't enough to get you compute optimal curves, unfortunately. It's too hard to solve because it's a Volterra equation. It's a fixed point equation. So what do you have to do? You need to simplify even further. But it turns out because you have a nice sort of understanding of the forcing in the kernel, you can actually represent the loss as basically the forcing function plus the kernel, where the forcing function, again, is like gradient descent on the problem, and the kernel is like SGD noise. So why is this useful? It's useful because, this we proved, it's useful because once you notice that you just have to know f and k. F and k are just functions of the resolvent. You're nice. Everything is spectral. Yeah?
So you could also just numerically compute the optimum, right, using those curves from
You can. But you will run into a problem numerically. At some point, you can't run it for large enough d. So you would like...
So you really want to know what the x is?
Yeah, because you will also have the same problem, which is that at some point, solving that problem will cost too much. Like, you won't be able to run it for very many d, especially big d. But it's a great question. That's how you verify all these things are kind of close to each other. I'm glad people are interested. OK, so how does this work? I'm definitely going to run out of time. The forcing function, OK, so now what we need to do is we know that we only have to care about the forcing in kernel. So what we have to do is we need to simplify those forcing functions. We need to understand sort of asymptotically what these behaviors are. And what we're going to see is that the forcing function will decompose into 3 terms, F0, FPP, FAC. I'll explain. And the kernel will be something nice. All of these things will be simple formulas. You can write them down. They're contour integrals. OK. But in their asymptotics, they'll be given by k to some power, d to some power. Okay, so what are these? We're in a random matrix theory class. This is a cool new random matrix, if you've ever seen one. Okay, this is a random matrix of the k hat where I've just projected into the spectral basis of d1 half beta hat. Okay, here. And what you see is F0, when you do this, is that k hat has a point mass at 0. And so F0 is just the point mass part at 0. So it's the limiting loss level that you will converge to, because you'll never be able to solve this point mass at 0. Okay? FPP are that because of your power law, you get little spikes here. So what FPP is these little spikes. Now, the problem is because you used a random matrix W, these are not exactly point masses. What they are is they're a little bit like a point mass with a Marchenko-Pasteur around it because of the W. And that little bit of like not being a point mass pushes things and creates noise, which obscures some of the signals. And so you end up with an absolutely continuous part, which is part of the bulk. Okay? That part we're calling FAC. Okay? Then, of course, we also have SGD noise, this KPP, which is just the excess risk due to 1 unit of SGD noise. Okay, so why is this important? This is important because back when people were doing power laws empirically and things, there was this idea that your loss looked like k to some power plus d to some power. Okay? This isn't exactly correct. Okay? What we did is we just took our loss and tried to approximate it. This is not actually the correct way to think about it if you're doing compute optimal. The problem is this k to the power, that's like my FPP, KPP, that's like the easy part. It's like solving those point mass part. S0, that's like my going k to infinity, that's like my limit loss value. Okay? That's F0. But there's a term, because of the embedding, which looks like k to some power, d to some power. Why is this important for compute optimal? If I plug in f over d, I get an expression which looks like this. And this term, depending on these coefficients and the exponent, can change my compute optimal. So we can't leave this term out. So this is just saying that the argmin can actually depend on this cross term. Okay, so that's pretty cool. So how does this work? Well, it turns out, that's basically the idea here. But your loss actually is even more simple. In fact, what ends up happening is that for various iterations, only one of those terms dominates. So you get FPP for some, KPP, FAC, F0 for some. And in fact, what happens is if you look in the alpha-beta phase plane, okay, for any one of these phases, some of these terms drop out. So let's take phase 2. You only get FPP, FAC, F0. KPP is too small. Okay? Makes sense? So this is what happens. You have 4 phases. Okay? So in phase 1, your compute optimal curves all look like FPP, F0. This is just capacity constraint, expressiveness of the model. But it only occurs in these regions, choices of alpha and beta. When you have phase 2, in this region of alpha and beta, all the loss curves look like FPP, FAC, F0. And the compute optimal will occur at FPP and FAC. For phase 3 and phase 4, you see KPP, which means SGD, is making its appearance. So in these phases, SGD matters. in the compute optimal. And the first two phases, they have nothing to do with the algorithm. They just have to do with basically gradient flow. It's a model problem. This is expressiveness of your model. This is embedding issues. You can do this. Someone asks it basically this. So you can run SGD. You can fix the flop count. You can try to approximate the exponents, like how the compute optimal d to the power should look, or f to the power should look. And you can match it with what happens from our theory. And it matches. Okay? Okay, so I'm going to go through these very fast, but just to say again. Okay, so in phase one, this is model sort of expressiveness constraint. Your compute optimal curve there. Okay, and you get a D star, which looks like these three in these different regions. P star looks like this in phase 1A, and they're different. But all in 1A, 1B, 1C, the loss curves look like that. Okay, you can match it, and it works. It's beautiful. I shifted the curve off a little bit so you can see the compute optimal. It all works. Okay. Phase two, this is the embedding causes problems in the compute optimal. Okay, the trade-off occurs where the embedding and the embedding, which creates a little bit of noise. So basically it says it doesn't pay to solve through the signals that are hidden a little bit, even though you could. It's too costly in compute. It's better to increase D. And you can get the compute optimal curve. All functions of alpha and beta. Works. See, it has these little kind of 3 regions. And your SGD. Isn't that nice? Yeah. In phase 3, KPP appears, which means SGD noise starts to become the dominant term. The compute optimal occurs where SGD happens. So it never pays, by the way, whenever you see an FAC term, it never pays to go through the FAC. It's always too expensive to do through the poor embedding. You can compute, and notice here you get an f to the 1/2. This is magical. How is this possible? Some complicated formula for the optimum, and then it turns out to be f to the 1/2. Weird. Okay. By the way, there's also a pentuple point. No idea. Everything matters at that point. So if you guys want to look at it, I have no idea what happens at that point. Everything is important. Okay? And you plot it, everything matches. Why is this important in terms of SGD? It might mean that a different algorithm will give you a different compute optimal curve here. This is because SGD is slowing your loss down. This is just to say that forcing function is not a good approximation for SGD, because here, and this is phase 1, we expect the forcing function to just be the only thing. It's just like gradient flow, should be the correct thing. But in phase 3, we see that the forcing function, which is this orange curve, is not approximating SGD very well. And we don't expect it to be a good approximation, because in this phase, SGD should matter. In phase 4, you can do the same thing. Now it's FPP, KPP, F0. KPP, again, SGD is in here. It's dictating the compute optimal points. Therefore, a different algorithm might change this region as well. Again, notice you do all this computation, and you end up with the most beautiful formulas. I have no idea why. But again, you see a D star f to the 1/2. Magic. Yeah.
Interesting. What was the explanation for it?
It's because when you draw the, if you want to think of it, draw the loss curve, you get slowed down by the SGD noise. So the SGD noise is like actually preventing you from speeding up in the algorithm, in the loss training part. And so it actually controls the compute optimal. Okay, all of this. Well, in some of the phases, SGD does nothing. doesn't appear, which is sort of like somehow the algorithm, it doesn't matter. It's more about model. In these ones, if you change the SGD noise, then you might change the compute optimal behavior. Yeah.
So in the cases where SGD noise matters, this is when beta is larger than alpha, or?
So it's here, phase 3.
Okay.
So this is when alpha is bigger than 1/2, and let's see, beta is bigger than alpha or something. Sorry.
Okay, so when beta.
Or yeah, beta is bigger than alpha. Thank you.
Yeah. So and just to remember, beta is the decay of the target, and alpha is the decay of covariance.
Yes.
Right?
Yes.
Okay.
So this is like data complexity. This is like target complexity.
So beta moving to the right is a more concentrated target.
Yeah, it's like 0. Yeah. Okay, I'm going to run out of time. Sorry. Okay. Yeah.
So normally we expect beta to be close to alpha when we do batching, right?
I actually think that's probably true. You probably are expecting, that's why you probably are expecting something in phase 3.
Because like when you batching, you pick up.
Yeah, no, there's, okay. Yeah, there's reason for phase 3. Yeah. Okay. It's fun to do this. You can go and compute SGD things and compute the exponent and then test to see how your thing goes across different phases. And you see that it matches. So the red dots are the SGD exponents. The different phases are the colored lines. So here I'm on the top, I'm fixing alpha varying beta. Okay, so I go through all the phases. I go through phase 3, phase 2, phase 1. Here I'm fixing beta, varying alpha, computing the exponents, and I'm going through phase 2, 3, 4, and 1, C. Okay. Oops. Okay. Give me a moment. One of the coolest things that you see, which is something that was shown empirically in Chinchilla's paper, is this universal scaling law. That is to say that this D star is independent of alpha and beta, had nothing to do with architecture and things like that, in some sense. Why? Because there's a huge number of choices of alpha and beta in the phase plane where that's the optimum thing to do. So as a practical thing, that's what you should do. You should just do that, because then you don't have to compute alpha, you don't have to compute beta. This is probably your best guess. And that's actually what chinchilla scaling does. That's where it comes from. Okay. I got some statisticians in here. They're going to say, wait a second, what are the finite D effects here? What is going on? What are the finite effects? Okay, so the first thing is technically I showed only that my loss was up to constant, the sum of these two terms. Just this first picture just shows that that's actually true. In fact, your constant is roughly like, I guess you can't see, it's like 1.2 or something is a good thing. Okay, so it's pretty good approximation. This is a warning to people who do empirical scaling laws where they do that D, varying D, and compute everything. Why? Because it's hard to tell if you're in the asymptotic region or not. That you're actually seeing D to some power, K to some power appearing. Okay? So what you can do to compute the exponents here is you can do like an instantaneous slope, and you can plot out what happened. And that's what's happening here. So these are instantaneous slopes, and that orange curve is what the actual theory says. And you can see that me at Google working could only get about there, and to get the asymptotics required out here. That's really far. So we are not in our compute thing at the right level. Like we need a lot more compute. We need so much more compute that in one of the phases, particularly phase 4, you need more compute known in the entire world right now to see the asymptotic phase occur, to see that you're getting D to some power, K to some power. More compute in the entire world. Technically not. Apparently California law just made something about D to like the 24, which is roughly what you need here. Okay, so they made some laws. So maybe we're not too far away from it, but it's going to be a while. Okay? And I'll just end there and say this is all based off of this paper. It's really cool. I'm trying to promote it. I think it's a great interesting problem that very little has been explored on theoretically, and it's super interesting. On a random features model, you have so much loss curve things. That's amazing what's going on. So thank you, and I'm sorry I'm over. Sorry.
So there have been quite a number of questions. We're going to take one more for the sake of time. You can talk to Courtney in the coffee break afterwards. Please go ahead. Yes.
Because in some sense, like the complexity of your model can be tuned by the scaling. Do you have something where you know what's the optimal choice of, I guess, beta given A or A given?
Oh, no, I didn't do any of that. We just allowed the, I mean, I guess you could do that. You could vary, we have all the formulas for every beta and alpha, so you could vary, yeah. This is hard enough. It's already 100 pages, and I didn't prove the two equivalences. So there's a random matrix theory problem out there for people. So.